Should I send a request to present?
Yeah.
I realized too late. Oh, I'm
I've sent
excited.
a request. Oh, yes, yes.
Why did we try again? You were so I like forgot. Oh my god. It was not that funny. No, it wasn't this girl. It's not funny. It was this. If I was French, maybe I would do it. Figure this out. Say how okay. Oh, I'm okay. It's not okay at all. Sorry. Sunglasses on. No, dude, it'll look like you're hungover. You're the only one. Why do you think any amount of sunglasses means someone's hungover? I don't know. You look at something like during chat, we have this like this summer thing right now. That's so many lectures back to back to back that my friend, she got on her English with my friend, she got stung like by something and she got a huge handkerchief. She was wearing sunglasses, but she realized very quickly she can like close her eyes and sleep and not pay attention. So everyone started showing up with sunglasses and they actually had to have a talk with us. They were like, guys, you cannot wear sunglasses. I didn't do really talks because they come on. They're like, we don't know about this. I'll tell you, can't wear the talk about it. We talk sometimes about shit. No. I'm touching that. Please. I'm gonna do it.
Let's take a look or do that somewhere.
Yes, let's make sense.
Okay.
Or actually, I can just behind you. That's fine.
It's fine, it's fine. You can look back at it. Running out of time. And sure.
Do you want us on the outside?
Yes.
Yeah. Okay, wait, we should move in. You don't have to fix yours. I don't. Sorry, what's your name? I don't think.
I'm Willem. I'm sorry.
We've never met.
I'm Willem.
Willem?
Yeah, Willem.
It's from my philosophy class and his first year of physics philosophy. It's my first one. Wait, you're his mentor?
No.
Okay, because how's we met? Okay, Roar we kind of met. Yeah. I know Kaylin knows the mentorship thing.
Yes,
Yeah.
sorry, that's why I asked.
Yeah.
I think we did exchange names once, but that was a while ago. We just broke off.
Maybe, yeah, when we did the same general.
Is it like that?
Yeah.
Did you say that was just philosophy? I think we have a proper version of it at this point. Oh, right. No, I like that.
Maybe I wasn't paying attention because usually when people say they're business philosophy.
I probably didn't. I said it just sorry, I misunderstood. No, I don't think I. I don't really think I.
First time.
No, I hadn't decided about that. Well, no, I would
numbers too.
It's like you haven't been out of
No.
No, not like that. Yeah, just fine.
Do you think you'll continue with doing all this stuff?
Yeah.
Okay.
See,
Because then you like find
Well,
more
in fact, I'm
content.
like,
I heard you're like not a fan of this project.
no, that would actually be
It's
the
like
worst case
No,
scenario.
that's
Wait, really?
that's blown out of proportion. I just said that there's something I like feels a strong that I enjoy more than this one. But I still don't like this. So yeah. It's all talk. Yours keeps blowing things out of proportion.
Yeah, so, nice.
Wait, are you gonna do research in atmospheric physics this semester?
So
Always coming, and maybe next year it's your turn to like go to your turn because it's a whole thing.
he's excited to see what I am so well. Oh, I am too. I started doing European rare, and then literally this was all so I never
The colloquium that I'm going to after this is like not as
first of all, it's
easy.
like,
Which one are you going to?
I'm going to economics.
I've seen it, but I've never had the time to learn. Do you want me to tell that too? Like I'm particularly going to go up to her and say, hi, my name is Winnie, and then Robin said this about you.
I'm so
I'm here. We might need an adapter, yeah. Interesting. I don't think I can see my mouse for some reasons. Can we try unplugging and plugging it in again? Or do you think you can connect with yours and I'll just like share with screen and Zoom? I can begin if I want.
Yeah.
Okay. All right. So, hi everyone. My name is Winnie, and today I'm really excited to talk to you about my past week. Okay. Okay, here we go. So I'm really excited to talk to you today about the research that I've been doing since last summer, titled Distance Measurement of the Kink region in the Orphan Chenab stream using our Lyrae stars. So I know that this is quite a mouthful. Wait a second. Here it goes. So first I'm going to break this down into 3 parts. Why do we even care about distance, particularly in near-field cosmology? And how are we going to measure distance? Spoiler alert, our Lyrae stars. And why do we care about distances to the Orphan Chenab stellar stream? And what even is that? And then I'll briefly talk about the data that I'll be using, how I calibrated it, and how I can compile that into a catalog with which I can use to identify our Lyrae stars with. And then lastly, I'll just briefly talk about the future steps. So first, we care about distances in near-field cosmology because it helps us to create a map of the local universe. And when paired with other information, such as kinematics, it helps us to trace back in time and to reconstruct galactic evolution. And there are multiple ways to measure distances, and the one that I care about is called our Lyrae stars. So our Lyrae stars are old and pulsating variable stars, and they can be typically found in globular clusters or dwarf galaxies. And as you can see on the left, these are the light curves for our Lyrae stars, and they have very distinct pulsating periods with which you can use the period-luminosity relationship and to find the absolute magnitude. And in my project, we care about using our Lyrae stars to measure the distance to the Orphan Chenab stellar stream. So the Orphan Chenab stellar stream started as either a globular cluster or a dwarf galaxy or something else. We're not entirely sure at this point. But what happened to the progenitor is that it orbited around the Milky Way, and under gravitational or like tidal forces, the stars get stripped, forming trails of stars leading and following the trajectory. And if there weren't any perturbation, you can see that the stream actually follows the trajectory very well. However, as you can see here, there is the LMC, the Large Magic Mountain Cloud, passing by, which perturbs the stellar stream and forms this kink region. So what we can do is, if we were able to constrain the distance to that kink region, we're able to constrain the Milky Way and the Large Magic Mountain Cloud mass. And there's actually been a previous study done where they use our Lyrae stars in the Gaia catalog to map the distance to the entirety of the Orphan Chenab stream. Then you might be wondering, okay, what are you doing with your project then? Well, as you can see here in the kink region, we estimate that the distance is about 100 kiloparsecs away, but in the Gaia catalog, the completeness of the our Lyrae stars drops beyond 80 kiloparsecs. So if we want to better constrain the distance to this region, we need to find a new and complete set of our Lyrae stars, which is the goal of my project. So what is a data set that I will use? My data comes from the dark energy camera, and it's based in Chile, and it's going to be taken in the R and I bands. And the data is taken over 22 fields of view, which covers the expected kink region, and then it's taken over multiple epochs. For example, in the R band, it's taken over 20 different times of observations. So my data set is quite immense. There are approximately 2.25 million sources per good epoch, and reminder, we have around 30 epochs. But we only expect to find 17 to 26 R Lyrae stars. So the goal now is, how do you actually find those stars? Well, there are multiple steps that I need to take. First, I need to construct a catalog, and I'll explain what that whole sentence means later. And then with that catalog, we will identify variable stars. And once we have the variable stars, we want to plot their light curves, and then to identify our Lyrae stars based on their distinct shape in their light curves. And then next, with our Lyrae stars, we want to find those that are actually in the stellar stream. So the first step is, well, I need to make some cuts on the data set first, because I don't care about oversaturated data points or spurious sources, or satellite tracks. So after we make a very general cut, we can convert the flux information into instrumental magnitude. And with the instrumental magnitude, what we want to do next is to calibrate that into a well-defined photometric system such that we can actually compare the magnitude across different times of observations. And once we calibrate that, we want to construct a multi-epoch photometric catalog. And essentially what that means is just it contains sources with the different magnitude observations taken across different times. And this is done just with something called cross-matching, where we associate the sources across different observations. And once that is done, the great news is now we reduced it to about 680,000 sources in our catalog, and these are likely real. But we still have a long step away from the 17 to 26 that we expect. So the next step would be to find those variable stars. And this just involves some statistics. First, what we do is, again, make some cuts. Because I want to find stars that are very faint, they're very far away, so I can just not look at the bright stars. And then I want to look at the number, I want stars that actually have a lot of observations. And because we know for our Lyrae stars, their pulsation amplitude is typically greater than 0.2, we can make that cut. And most importantly, we do something called the F2 statistics. And if we have F2 greater than 3.1, that just means that we're 99.9% sure that the source has a variability in their magnitude. And that gives us, 11,000 variable sources. So great news for me. Because now, if I were to just create the light curves, and then to look at these light curves, I have less sources that I have to go through to find our Lyrae stars. And so here, I just want to remind you guys what our Lyrae stars look like. And so they look like this. So on the left, you see the phase-folded light curve of our AB stars, and on the right, you see phase-folded light curves of our C stars. So what's important about these light curve is that it's phase-folded, which means the observations taken, which is different from magnitude over time, because on the x-axis we have phase, which is which phase of the period at which a magnitude is being observed. And note that we do need the period information to create beautiful light curves like this. So, because that brings us to our first problem. Because we don't know that period, we only have magnitude over time. So we need to use something called the Lomsdorff periodogram, where essentially it tells you what is the best frequency or the best period that fits to your data. So on the bottom row, you have on the y-axis, you have the Lomsdorff power. On the x-axis, you have the period. And whichever period that has the highest power just means that, this period is most likely to be the one present in your data. And if we were to implement this, on the left, you have the Lomsdorff periodogram. You can find a period that has a very high peak, and then to phase-fold based on that period. And you can see here, our data is much nicer. Once it's phase-folded, you see a very nice sinusoid. And of course, you can see that there are a lot of peaks on the left there. And which one is the right period? And why do the differences between their frequency look like the same separation? And that's because of our second problem, which is called aliasing. So you have an original signal, and because of undersampling, you can fit your data with different frequencies, and they look equally nice, and it makes signal look like they have either longer periods or shorter periods than they actually have. So in order to determine that period, so yes, the peaks here that you see, all of them are aliases of one another. So how do you actually determine the periods? Well, first, you want to make sure that the peaks that you see are actually significant. So if it passes that dashed line, that means that this period is significant. And you need to make sure that you want to remove all the aliases. So you start with the peak with the highest power, and then you remove all the other peaks that are aliases of this peak. And with that, sometimes with that, I will select the top 3 periods that are significant and not aliases of each other. Sometimes there's less than 3 periods. For example, like this one. But I am able to faithful that when I have this period and have a nice light curve right there. So this one is actually a RRC star. So RRC star light curves are generally very sinusoid and looks like that. And here is a RRAB star in my catalog, where you can see there is a very sharp ascent in brightness and then a very slow decline. And as the brightness increases again, there's a little tiny peak again. So this is how you distinguish, okay, this is a RRAB star. And now I kind of want to pose this question to you, because do you think these two are Lyrae stars, and what type could they be? Any takers? No? Okay. So these two, in fact, are both Lyrae stars, and these are all RRAB stars. But they don't look as nice as the ones we saw before, and that's because, if you can see here, this source right here, this one right here, it's the only one that kind of throws you off, and that's likely because, okay, maybe I did something wrong with cross-matching, maybe 2 different sources are associated as the same, maybe the calibration was wrong, but because it's only one, but if we were to just ignore that source, we are able to see a very nice RAB light curve. And on the bottom, what happened is just we got kind of unlucky where we didn't observe this star when the pulsation, when the magnitude is increasing. And of course, these still look rather nice. In my catalog, there's still stars, there's still variable sources that look quite ambiguous. For example, on the top, this one might look like it is an Lyrae star, but because of how faint it is, there are some huge error bars, and then there are not as many observations. And on the bottom, this one looks like it could be an RAB star, but if you were to look at the trough, it's sharper than what we would expect. And actually, the one on this row, you would expect it to be, I would expect it to be actually a binary star. And of course, I kind of skimmed over this very crucial question of what exactly is the right period? Because as you see here on the top, the peaks are relatively have relatively the same power. So which one is correct? I can't just say, okay, that one has slightly higher power, so it's the correct period, while all of them give really similar looking light curves. So that's a problem that I'm tackling with right now, where I'm using the Bailey diagram, which is essentially the relationship between amplitude and periods for our Lyrae stars. And I'm going to look at, okay, what combination of amplitude and period looks like which combination is right for an RAB star or for an RRC star. And so that is what I'm doing right now. And in the future, what I have to do is finish off identifying our Lyrae stars once I have a confident period. And then I want to find the stars that are actually in the Orphan Chenab stream. And the 5th step would be the final step, which is to just calculate the distances to these Lyrae stars. And just to briefly wrap up and to summarize what was talked about, we first looked at, okay, why do we even care about distances in near-field cosmology? And it's because it helped us map the local universe, and it helped us create models of the galactic evolution. And one way to measure distances is through our Lyrae stars. And in my project, I'm going to use our Lyrae stars to measure the distance to the Kink region of the Orphan Chenab stream, which will help us to estimate the potential of the Milky Way and the LMC. And then, with our data, we need to calibrate and to compile a multi-epoch photometric catalog, with which we use to identify variable sources with the F2 statistics. And then the next step would be to use the long scale periodogram, which we found the pulsating period of these sources, and we created phase folded light curves with which we use to find our Lyrae stars based on their distinctive light curve shapes. And that is it for this presentation. Thank you for listening. Any questions?
Why did you say, I'm not an astro, so maybe
Yeah.
this is just knowledge that I don't know, but how do you know the expected number of our Lyrae stars every?
That's actually a good question, because let me just go back to this plot. So in this previous study, they used Gaia RLR stars, and because these regions are actually within that 80 kiloparsecs, so we know approximately how many RLR stars are in this region, and then if you assume that there's a uniform distribution of the RLR stars, then you can kind of estimate how much you expect there to be in the region at which Gaia can't probe completely.
That's super cool, thanks.
Anything else? Oh yes, hi.
Do you know why the RAC and RAB stars, their period graph looks different? Is there
Yeah.
a reason for that?
Yes, there is. So they're different because of their pulsation mode is a bit different, and that kind of just goes into what these kind of stars are made of, which evolution phase they are in. For RAB star, they call it fundamental mode, which you can just think of as the most basic kind of pulsation. While for RC, it's like the first overtone mode, which is there's something else along with that basic. You can think of it as like a superposition of two different types of pulsations. But yes. Yes.
I'm sorry if you said that I missed it, but how did you decide on what was the right period for this study?
So let me just go back to the next slide. So that's a good question because it's a very layered process. Okay, here we go. So first, I need to find that. Let me just zoom in. First, we need to find that the periods are actually significant, which just means that how likely is it that it's just a false alarm? There's no actual pulsation or periodic periodic things in my data, and which is this threshold here. And you look at the peaks with the highest power, which means that these frequencies are likely to be the ones present in my data. And then because those frequencies might be aliases, I need to determine which combination of the pulsation amplitude and period. Like for example, if I know my star has a pulsation amplitude of 0.8, then I know that the period must be within 0.6 to 0.8 days. So, yes. Anything else? No?
That's all. I think I'll skip it once again. Next time we'll talk about Isabella, Liang. I'm trying to remember one. Try this again. Yeah. And also there's a Zoom meeting there.
Okay. But it's just because the pulsation is different, and the reason for it is different. This star, it's which stage of evolution they are, what is the argument? And are they both? So yes, they're all RLR stars, and they're looking for all of them.
Okay, so this is the code.
Yeah. So they have
password is password is 327.
Okay.
Oh,
Give me 1 second. It's okay. Invalid meeting link, it says. Can I try it one more time? Juan Mena para. Great. Okay, so before we start, I just want to talk a bit about what are FRBs. So FRBs stand for fast radio burst. They're called this because they're fast, as they are only in millisecond duration periods. They emit in radial light, and they are a burst of energy. Another thing about fast radio bursts, or FRBs, is that they are extragalactic. When I say extragalactic, I mean that they don't necessarily all come from within our own galaxy, and we can tell this through a measure called dispersion measure, or DM. Essentially what that means is that when the burst happens, it has to pass through a certain amount of gas and stuff in the way from the origin to our telescope, and the amount of stuff that it's passing through is more stuff that's within our own galaxy. Furthermore, it must come from outside. We can kind of see this with the graph on the left. This is an image, or a graph made by Duncan Lorimer, who was the first person to discover an FRB, and you can see this kind of curvature shape in this graph, showing that distortion of the signal because it's passing through all of this stuff. Two very big questions about FRBs is, one, they have unknown progenitors, meaning we don't know where they come from, and two is repetition. So we see this period of some FRBs, meaning that a burst will occur, and some amount of time later, the burst will occur again in the same location from the same source. However, we don't see this within all FRBs, so it's still a very big question of if this is an inherent property of FRBs as a whole. Now comes the question of how are we detecting these FRBs? And at least what my team uses is something called CHIME. So CHIME is the Canadian Hydrogen Intensity Mapping Experiment, and it's a transit telescope located in Kink, British Columbia. When I say transit telescope, I basically mean it's a telescope stuck to the ground and it has no moving parts. So it's constantly just looking at the sky. Just in regards to how it's made, so it's comprised of 4 long cylinders that are 20 by 100 meters in length in the north-south direction. In terms of its observing band, we're observing at around 400 to 800 megahertz, and CHIME in general is really great for FRB detection. it originally was not designed to detect FRBs. It was designed for more purposes within cosmology. However, when we turned it on, we saw that, wow, it's actually a it's very good at detecting FRBs. Just to kind of prove this point to you, this is a graph on the X is just the amount of years from 2012 to present times. And then on the Y is just how many FRBs we have found. So this orange line is just every other telescope in the world that detects FRBs. And you can see this very steep line starting around 2018 when CHIME turned on. And we're detecting, or when CHIME turned on, we went from detecting on the order of tens of FRBs to on the order of now thousands of FRBs. Currently we have detected around 4,000, more than 4,000 FRBs, of which 80 have shown to repeat. Awesome. So now it comes to what are sidelobe FRBs, which is what my research involves. To explain this, I wanted to talk about an analogy with this flashlight. So CHIME works, you can think of it like a flashlight. When you turn on the flashlight, it has this very sensitive region, very bright, as you can see here, and that is what we define as the main lobe, or the main beam, I should say. This is a region when we look up straight at the sky with CHIME, spanning around 2 degrees on sky from the telescope at 800 megahertz. So what that means is that if an FRB happens in the main beam, we're very sensitive to that area, so we'll be very likely to detect it. However, much like a flashlight, although it is very sensitive in the main beam, as you get towards the edges, you're still able to have some sensitivity. However, it's just not as great. And this is what we define as the sidelobes. Sidelobes in terms of CHIME are defined just as greater than 5 degrees off the meridian in the east-west direction. Just to talk about sidelobes a bit, since there's such low sensitivity, in order to see an FRB within these regions, it needs to be very, very bright. And it's not a common occurrence in which we see an FRB there, just because it has to be very bright to be able to be seen within these two regions. Now this is just a graph, kind of talking about the same thing I was saying. So on the x-axis, we have something that I call hour angle, which in essence is just how far away you are from the main beam, 0 being right directly overhead, the most sensitive region in CHIME, and then the further out from 0, the more you enter the sidelobes. And I should also say on the y-axis, it's essentially how sensitive your telescope is. So in the middle, around 0, spanning around 2 degrees, is my main beam. So as you can see, we're very sensitive to that region. However, when we go out of the main beam, so greater than 5 degrees on both sides, we're entering the sidelobe regions. So these more sensitive areas. So now that you hopefully understand a bit more about what a sidelobe FRB is, why do we care about it, and why are we even doing research in it in the first place? And it really comes down to these 3 key aspects of sidelobe FRBs. One is that, like I mentioned before, in order to detect an FRB in this region, it needs to have a high intrinsic brightness, since we're in such a low sensitivity region. The second thing is just the quality of CHIME having such a long exposure time. So CHIME is observing 24/7, and that helps a lot with detecting these sidelobe FRBs. And finally is that FRBs that happen in the sidelobes most likely have or do have nearby progenitors. And this is by assuming a common luminosity function, which in more simple terms basically just means that the brighter the FRB is, I'm going to assume that it's closer to me. And since FRBs in the sidelobes are so bright, by the property they have to be bright to even be seen, they're most likely going to be closer, meaning I can study their progenitors, aka where they came from, much easier. And by having these facts about sidelobe FRBs, I'm able to understand more about all FRBs as a whole. So specifically, some of the big questions like their host associations, where are they coming from, what's causing these FRBs, and also their repetition. So do all FRBs have some periodicity to them? Okay, so I work in a working group, so it's not just my work, but also many different scientists around the world. So I just want to talk a bit about what we do as well as specifically what I do within that working group. So this is just like a pyramid of everything we have done. I'm just going to be focusing on the bottom and then the right side, so this blue and green part, since that's the work I do. So what we did at first is we built a real-time sidelobe classifier. So this was designed by another student, and what it essentially does is that it's able to tell us if an FRB we detect occurs in the sidelobes. So once we know it occurs in the sidelobes, we do a source image localization. And what that means is that I'm using something called visibility data to generate source images of that sidelobe FRB. The next thing we do is an n-squared localization. So once we have our image, we're able to find its actual location within the sky to a lot higher precision. And then of course we have our VLBI and calibration and validation. If you're curious about that, I can talk about it in the question period. Before I begin, I just want to talk a bit about the difference between baseband and n-squared localization, since if I just go back here, you can see my work with n-squared is very much aligned with baseband localization. We're very much on the same level. And it's kind of because we're doing the same thing, but just in two different ways. So what baseband does is it's essentially a way of telling the strength of the signal. So how strong is the signal that the sidelobe FRB is coming at to my telescope. An advantage of baseband is that it's very fast, since we're only considering the strength of it, so the voltage squared. And one downside is that we have to use pulsars, since we know their location very well. And there's not that many pulsars within the sidelobe regions, so I'm restricted to a view of only going into a set amount of points on the sidelobe region. So I'm limited by hour angles. And once again, hour angles is just how far it can go within the sidelobes. Now, n-squared data uses steady radio sources. So what it does is it tells us the strength of the signal as well as the location of the signal through a property called cross-correlation. This is a lot more useful. The only downside is it's more slow, just because it's more data intensive. But it allows us to sample a much larger field of our sky. So it allows us to go further into the sidelobe regions and do more localization there. Great, so now just talking a bit about my specific project, I wanted to start with my research question, which is how well can we localize sidelobe FRBs using interferometric visibility data, and what are the systematics that are limiting us? So before I begin, I just want to talk about the data set I'm using. So like I mentioned before, for n-squared localizations, we use steady radio sources. So what I'm doing in particular is I'm using Cassiopeia A, Taurus A, Virgo A, and Cygnus A, which are all depicted here. And then here's just a little table on the bottom indicating their RA and DEC. And for those that don't know, RA and DEC is just basically a way to pinpoint locations on the sky in astronomy. So think of it as your longitude and your latitude. So for my project, I'm trying to test different systematics. And what I mean by this is just different scenarios I can change CHIME to improve our localization. So this is the first scenario, scenario A. And it has to do with applying a shift in the north-south baselines as well as the east-west baselines. So like I mentioned, CHIME is 4 long cylinders, and this one is changing it with delta y and delta x, doing an overall just a rotation of an angle. In scenario B, it's just a pure vertical shift in y. And these two equations are just very well defined within the literature, so that's what I chose to use. Now just to dig into more of the results I've been getting, let's start with scenario A. So this is a visibility localization plot. This one specifically is of Taurus A. So we have our red point kind of in the middle. That's the true position of Taurus A. These green lines represent the RA and DEC of where it is in the sky. And then all these purple points are just my n-squared data. So this is raw data. I've done no correction. I didn't apply scenario A to it at all. When I do apply the correction, I get this plot. So you may have seen, I'll just go back one more time. So this is no correction. Correction, you're seeing the shift left. That's improving this RA localization. And we can better see this through this graph. So this is no correction. We have hour angle on the x. So once again, how far away I am from the main beam. So the greater you are away from 0, the more into the sidelobes. And then RA, no correction. When I apply my correction, I'm seeing the shift downwards, closer to the line. So that's good. When I talk about declination, once again for the source, this is no correction, correction. And if I go back one more time, no correction, correction. You're not crazy. There's basically nothing happening. There's no change. It's not really improving. It's not really getting worse. So the next step is to compare with basebands, like I mentioned before. So all of the baseband analysis is done by Chessie, another student at the University of Toronto. So this is the plot I just showed you on the left with no correction. This is her same plot, but with baseband data on the right, also with no correction. When we apply both of our corrections, we get these plots. So you could have noticed that if I just go back one more time, this is her original plot on the right, and then when I go do the correction, that we're both seeing the shift left, and it's improving our localizations. However, at least in the case of basebands, we're getting a worse localization for declinations. It's becoming much more spread out. So just as a summary, both of the localizations are improving in RA. However, in declination, it's just remaining stagnant for n-squared data, and in baseband, it's worsening. So that was scenario A. Now I moved on to scenario B. So this is a plot showing Cassiopeia A, so one of the steady radio sources I talked about. Our angle again on the x and just the change in declination on the y. So all of these blue dots are basically me applying the shift in y, so scenario B's corrections. And then all of these red points are me applying scenario A's corrections. From this little dashed line, which is where we want all of our points to be as close as possible to, you can probably tell that all of these blue points, so by applying scenario B, it's much closer to this horizontal line, meaning that it is a better localization than the rotation of negative 0.071 degrees, aka scenario A. When I look at RA, same thing again, my scenario B and scenario A overplotted in this horizontal line. There's not much happening, there's not much improvement, there's not much worsening in either of the scenarios. So overall, these are just some statistics. I'm seeing a better localization when I apply scenario B. So this is once again just the pure Y shift, specifically in declination. To put a number on it, doing a scenario B is improving my localization by 25%. And then the last thing I just want to talk about is Sidelobe FRBs, like I said in the beginning, are great for host associations. So finding where these fast radio bursts are coming from. This is a result from my colleague Chessie when she used baseband. So she used one of her localizations and pinpointed it to this galaxy, which I just thought was a really cool graph to show to tell us that doing all of this, these little systematic shifts, is improving our understanding of where fast radio bursts are coming from. And yeah, that's it. Thank you very much.
Are there any questions?
Yes.
Can you go back to the scenario A versus scenario B slide?
Yeah.
So these equations, are they just, like for example, 2.73 for example, are they just like givens in literature, or is there like a physical reason as to why
They
choose
are,
that?
yeah, that's a great question. So they are given in the literature. These are very, very well-defined shifts. The derivation is very long. However, it's just very well known, and this is shifts they applied in the main lobe. So given they were applied in the main lobe, that gives us enough just reasoning to also apply them in the Sidelobe region. Yeah, no problem. Yes.
I know you spoke briefly, it wasn't too much of your topic, you spoke briefly about localizations. I kind of just wanted to ask more about that and how the localization process is done.
Okay, yeah, so that's a great question. So just kind of going back to the graph of what we all do, this one. So the way the localization is done is we're first doing, like I said, this Sidelobe classifier. So we're taking all these FRBs that we see in CHIME, and we're saying these ones happen in the Sidelobes. So once I know those happen in the Sidelobes, I'm able to create a source image, which I can show here. So this is what a source image looks like. I can't remember which source this is for, but it's one of those where I was talking
Could have
about.
made it out time for you.
Yeah. So this is what an image would look like. And once I see that image and I process it throughout its entire transit meaning as the amount of time I see it pass through CHIME, I'm able to do, this is an error bar slide, but I can just talk about it, to do a Gaussian fitting, specifically a 2D Gaussian fitting of the source, and then take essentially the strongest point within the source transit graph, image, to find the location of the source.
Perfect, thank you.
No problem. Yeah. Okay.
Thanks. Think of speaker again. Next up we have Simon Tai.
Would that be after the break, right?
Yeah, right, but we should just not say.
Yours too. Yours was also very cool. Like, I don't understand all the star stuff, but it sounds awesome.
3,000 light years away, at the center of the Butterfly Nebula, there lies one of the hottest stars in the galaxy. It blazes with a temperature over 40 times that of our own sun. And yet, not far from it, we find CO2 at a temperature as low as 20 Kelvin. Right? Hello all, my name is Simon, and my summer research project was the modeling of CO2 in the butterfly nebula. So, let's begin. So first of all, what is the butterfly nebula? So it is a planetary nebula that lies over 3,000 light years from Earth in the constellation Scorpius. And the primary thing that we focus on is the central star, which is responsible for the nebula's appearance. So it is a dying star with a surface temperature of over 250,000 Kelvin. In other words, it dying has been casting off layers of gas at a speed of close to 1 million kilometers per hour, which is responsible for the nebula's wings. The entire thing has a total wingspan of around 3 light years, but for my project, I only focused on the central region right there. And for the data that I'm actually working with, well, it's on the left right here. So this is the photon flux distribution of the butterfly nebula at a particular wavelength. And for some spatial recognition, this gap right here corresponds to that. So throughout the majority of the project, my goal was to analyze an anomaly in the 14.8 to 15.4 micron range and try to model this feature. So what you're actually looking at here is an emission spectrum. As we know, different molecules, atoms, compounds, they will absorb and emit different wavelengths of light that cause their electrons to go up and down temperature levels. And this is one of the notable absorption wavelengths of CO2. But let's not move so fast, because we're not even sure that this is CO2 yet. We can directly compare it with one of the CO2 models, and it looks quite similar, but of course we aren't happy with just that, and so that marks the beginning of our project. So to model that feature, the goal is to go through just a couple of steps. The first step, we need to fit something called a continuum. This is basically modeling everything else but our CO2, because then we want to divide out by this continuum to only retain our CO2 signals. Lastly, we want to fit it to some models, and that will tell us some things about the CO2, like the temperature, how much there is, how fast it's moving, and more. But unfortunately, these steps are a lot easier said than done. So after a lot of different attempts, going from using a polynomial, using a spline, I even spent time trying to train an AI to do this, I finally reached a continuum I was happy with. So now we divide up by this continuum, we get a normalized spectrum, and now it's time to fit our models. But how exactly did that work? So our models have 4 parameters associated with them, which we try to optimize. So we first have the temperature. So this is just how hot our CO2 is. And as you can see, it affects the spread of the absorption lines, with the spread increasing as the temperature goes up. The reason behind this is just that as the CO2 gets hotter, it moves around faster, and some gets red-shifted, some gets blue-shifted, so the absorption lines, they spread out. Next, you've got your column density. That's essentially just how much CO2 there is along your line of sight. So this, as you can see, this will affect the depth of the absorption, with more depth corresponding to higher column density. And of course, this makes sense. The more CO2 there is, the more absorption. Then you've got your radial velocity. So this is just how fast, as a whole, the CO2 is moving towards or away from us. So a more positive radial velocity leads to redshift, a more negative radial velocity leads to blue shift. And lastly, you've got your black body temperature. So this is basically your background temperature. It does affect the depth of the absorption a little bit, but as you can see, I had to zoom in quite a bit on this image just to see that tiny difference. So actually, at the low temperatures that we are at, we can completely disregard that parameter on our left. And to finally actually fit these models, well, it just reduces to minimizing a chi-square value. We calculate the chi-square across every possible combination of these 3 models, and when we take the minimum, we find this model as the best possible fit. And but so far, I've only shown you a singular pixel in that region in the Butterfly Nebula. So let's take a look at some of the others. So here are 4 other pixels, and we can go through the exact same process. So we first of all, we fit a continuum, we divide up by this continuum, and lastly, we fit it to some models. So this, you can see that they each tell you different things about CO2. This one says it's at 20 Kelvin, that one says it's at 30 Kelvin. And as you can also see, some of the fits, well, they're not perfect. And that's actually perfectly fine, because our models are very simplistic, and the environment is very, very complex. It is littered with more than just CO2. It comes with a lot of different other dust, a lot of different other molecules. They each have their both emission and absorption, and our simplistic models, they cannot capture everything. But what this does allow us to do is this does allow us to create just regions or pictures of how parameters change across our region. So first of all, for our column density map, you can see that the column density is highest around that blue and black region over there, and becomes smaller as you near the edge. So this just tells us that the CO2 is the most near that central region, and it's lesser as you near the edge. Next, you've got your radial velocity. So from here, you can sort of see that there is this central colored arc right here. And we believe that this corresponds to the torus around the central star. And lastly, we've got the temperature. So as promised at the beginning, despite the central star being so incredibly hot, we find CO2 at a temperature as low as 20 Kelvin here. But now we have to answer the question, right? So why in the world is the CO2 so cold? Well, we think that it's because of the torus around the central star. So around the central star of the Butterfly Nebula, we have a very dusty torus, with that being the front side of the central star and the back side. And we believe that the CO2 lies on the very front. As a result, when light tries to reach it, can't, and so the CO2 becomes really, really cold. But many of you might have noticed something. At the beginning of the presentation, I said I was analyzing the entire 15.4 micron range. And so far, I've only shown you 15.2. Well, that's because so far, I've been trying to hide something. But now that all of you know the context, well, I can show it to you. But first of all, can anyone here tell me what the freezing point of CO2 is? No? Well, it doesn't really matter right now. And it also changes depending on how much CO2 there is, your conditions, it changes about on everything. But at a temperature as low as 20 Kelvin, I think it'd be pretty reasonable to say that there might be ice here. And so we began our search for CO2 ice. So first of all, we need to revise our continuum. Previously, we were using this continuum because our gas, CO2, has very narrow absorption, as you can see with that very narrow lines. But ice, CO2, has much broader absorption, which we try to capture using this continuum. And then we need to go through our process again. So first of all, we need to fit a continuum. We've already done that. We need to normalize the data again, but now we need to add an extra step. Because we've already fit our gas phase models, we can divide out by the models to find out what's left. And it turns out that what's left is we try to fit a CO2 ice mixture and find out that, well, it's not a bad fit. And now we're ready to fully model our data. So we start off with a continuum, we multiply it by our ice model, and then lastly we multiply it by the gas model, and in the end we achieve quite a good model of our data. And still the project, well, it's nowhere near done. So I have left the work of this project by now, but there is still a lot of work left. Well, one can look at the entire spectrum instead of looking at that narrow range, which is that tiny bit right there. And we're going to try to model more broad features, like the one that we saw, to try to determine what the exact composition of the ice might be, and also determine dust features that will heavily affect our results. And last of all, of course, there's the obvious question, which is that why should you all care? So CO2 ice, well, this is the first detection of CO2 ice in a planetary nebula, and previously it was believed to be, well, completely impossible. Since planetary nebula are very harsh regions with heat, radiation, it's everywhere, that makes it very difficult for anything more volatile than water ice to form. And even we found that, I didn't go through too much about this, but the gas to ice ratio of the CO2 is very different than what we find around young stars, and that leads us to believe there is some complex forming process of the CO2 that we've yet to understand. And moreover, we need to suddenly consider a lot more of a planetary nebula in the contribution to space chemistry. And the reason why is that when UV light hits these CO2 ice mixtures, along with also water ice and ammonium ice, you can get very complex compounds forming, like amino acids and other things that is actually necessary for life. So who knows? Maybe an asteroid went through a planetary nebula in the past, and that's how life on Earth had come. But that's just a lot of speculation. But I do think that this could mark the start of something. I look to the future, and I'd love to see what the rest of the scientific community can do with this. So, last of all, and to conclude, we detect cold CO2 in a planetary nebula, and we report the first detection of CO2 ice in a planetary nebula. And of course, this would not have been possible without my research supervisor, Dr. Yang, and two PhD candidates that I worked with, Charlie and Nicholas. All right, so that's the end of my presentation. Any questions?
In like the full spectrum, like the early wavelengths, you have like negative flux. Do you know what that can mean?
Well, the explanation behind that, honestly, I don't actually know since I didn't focus on that part for this. Sorry.
No more questions. That's
All right.
speaker here.